Good afternoon, everyone. Welcome to the ITS weekly seminar. And today we're delighted to have Professor Dan Watt to give us the seminar. Professor Watt is with the Department of Civil and Environmental Engineering and the Department of Electrical Engineering and Computer Science and the Institute for Software Integrated Systems at Vanderbilt University. Before Vanderbilt, he was on the faculty of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign, and he had visiting appointments at Institute for Pure and Applied Math at UCLA, Microsoft Research at Redmond, and Nokia Research Center at Palo Alto, California. Dan's research on automated vehicles has appeared in numerous media outlets, including ABC's Good Morning America, Reuters Wired, and MIT Technology Review, among many awards, and he has received the prestigious National Science Foundation Career Award in 2014, and also was named a 2018 Gilbreth Lecturer by the National Academy of Engineering. Dan, with that, I'll give the Zoom room to you.
Well, Michael, thanks for the introduction. It's really a pleasure and an honor to be here with you and the students and the folks online. It's really excited to talk to you about some of the work that we're doing in traffic flow smoothing. And to try to summarize the talk in a nutshell, basically what we're trying to do is take some of the technologies that are now available on commercial cars, like level 1 and level 2 vehicle automation systems, and trying to figure out if there's any way that we can modify those things so that they're not just good for drivers, but that they might also have benefits in aggregate to the traffic flow overall. And so what I'll walk you through today is some of the work that we've been doing to try to get to that point where we might be able to eventually achieve traffic flow smoothing at scale. But before I get into kind of the details of why we're doing that, I want to kind of set the stage for where our research lives and what our research will and will not solve. So this really started when I moved to Nashville in 2018. There was a discussion about whether or not Nashville, a very rapidly growing city in the South, should invest in public transportation. And there was a lot of opposition to the referendum that eventually failed. And the thing that probably bothered me most is that there was a comment that something like solving congestion with public transit was solving a 21st century problem with a 19th century technology. The heart of which was really like, well, autonomous vehicles will be here in a moment. They will be able to, run fleets of these vehicles that can get us to wherever we want, whenever we want. That will be so much more convenient than waiting for a bus. Why would we ever want to invest billions of dollars in public transit? Autonomous vehicles are going to cure congestion. Now I'm ad-libbing a bit here to make the point a bit more extreme, but everybody who is involved in transportation knows that congestion, the typical Google Maps that I've got in the background, it is the imbalance of demand for travel and what the infrastructure can supply. And it can be out of balance with regular drivers, and it can be out of balance with autonomous vehicles. What's important if you want to try to predict what autonomous vehicles will do for congestion is you need to be able to predict kind of both of those consequences. What's it going to do for the demand, and what's it going to do for the supply? And probably one of my favorite studies in this area is this question about like what will happen to the demand. And basically, the challenge is that we don't have fleets of robo-taxis available today to experiment on. So what can you do? Well, you can do the next best thing. You can give drivers a chauffeur, for a week and set number of hours that they're allowed to use that chauffeur and see what happens. And I just love this study because its directionality, it must be correct, right? If you gave me a chauffeur, I would drive more. I'm sure of it. What I think is interesting in terms of the cohorts, you get more miles traveled overall. You have retirees that are traveling more, which I think is actually great. You're providing access. The problem is that you're providing them in potentially single occupancy vehicles at potentially congested periods of the roadway. And at least in Nashville, I tried to make this point stick to folks is that, if you're frustrated in traffic today, imagine that fully autonomous future when the car in front of you has no one in it. People in this study, as I think is natural, right, would actually send people on their way to go run errands, right? Anytime you have the chauffeur go pick someone up to do something for you and you're not in the vehicle, that will be in the future no one in the car, no chauffeur. It'll be a completely automated trip. So those ghost miles would literally be vehicles that are completely empty, still delaying your commute. So that's only one side of the puzzle. The other side of the puzzle is what happens on the supply side. And it's true also that autonomous vehicles or automated vehicle technologies put on vehicles can increase the capacity of the roadway. This was most famously demonstrated in the Berkeley Path Automated Highways project, where the fleet of Buicks in the top corner were basically connected together with wireless radios, and those vehicles exchanged information to drive at very high speeds, very close together. And the punchline for this was that effectively by adding those technologies to the car, you could double or triple the capacity of the freeway. In other words, you could get a freeway which exists on top of your freeway, for nothing more than changing the way that the cars are automated and communicate together. Of course, this is in ideal conditions, and there's all kinds of disclaimers that go with that. But the more likely pathway forward for this type of technology is actually on the trucking side. So the bottom video is one that comes out of some work that's been a collaboration of KTH and Scania trucks in Europe. And they're using the same kinds of ideas, much more modern this time, to get freight vehicles to drive very close together at very high rates of speeds, not for capacity, although it can help, but primarily to improve the aerodynamic drag for the vehicles that are in the second and third in the platoon and saving them fuel. These two examples both are highlighting one important fact, that if you want to increase the capacity, one way to do that is to move people or goods at very high speeds, very close together. If you can get more vehicles in the same space as fewer vehicles, you're going to increase the capacity of the roadways. Kind of set a little bit of math to explain how this works, right? If you've got a bunch of vehicles, we'll keep it simple. Assume they're all the same length L, assume they all travel at some speed V, and assume that the distance between the front bumper and the rear bumper of the car ahead is a fixed delta X. Well, we refer often to the spacing of the vehicles as the front bumper to front bumper distance. That's nothing more than delta X plus L. And if you want to know what the density of traffic is rather than the spacing of the vehicles, spacing of vehicles is like how much distance per vehicle. The density is how many vehicles per distance, how many vehicles per mile. It's a natural way to talk about traffic in terms of the density of the flow. And the density is related to just 1 over the spacing. Okay, from the flow density, basically from fluid mechanics, we know that the flow is equal to the product of the density times the speed. And recognizing that the density is just the inverse of the spacing, we can rewrite the flow on the freeway as the velocity divided by the space gap, delta X, and the length of the vehicle. So this is important because it's now relating to us the speed of the vehicles and the space gap between them. Those Buicks in that last video have a very small space gap traveling at the same speed that humans do. And as a consequence, they increase the capacity of the roadway. So if you want to increase the capacity of the roadway, you can either increase the speed and keep the spacing fixed, or reduce the spacing and keep the speed fixed. And I guess it's possible you could reduce the size of the vehicle, but if you're not going to play around with that, that's basically the only things you can do. Make cars drive faster or make them drive closer together. And those platooning technologies are ways in which you can get the cars to drive closer together. So if you kind of extrapolate this to the classical models that we use to characterize traffic flow, you end up with a model of how dense the traffic is, or the inverse of the spacing, versus the speed that the vehicles are traveling. And that gives you the fundamental diagram that shows you that as the density increases, if the speed is fixed, you're going to increase the flow to a point, at which point the roadway gets over its capacity, and you start seeing congestion appear. If you have automated vehicles that are driving with larger spacings at the same speed, you could end up with this kind of red speed density model here, which is actually bad for capacity. It's going to reduce the total flow on the freeways by having a bunch of automated vehicles that drive very conservatively relative to humans. On the opposite end of the spectrum, you could have vehicles that are automated that drive at much closer spacings at the same speeds, and those are actually good for capacity. They're going to allow us to get more vehicles through the same freeway than what we can do if it's only under human control. Again, the core idea, move people at high speeds close together. Well, a way you can build a freeway on top of a freeway without doing anything on the technology side is picking up another person. If you carpool, you can double the capacity of the freeway if everyone does it. If you pick up more people in your car, you could 4x the capacity of the freeway. The point here is that the goal should not be to move vehicles per hour, but people per hour. And as soon as you open that to the goal of your work, then there are many other solutions, some that are technology enabled and some that are not, that can still help you achieve miraculous improvements in what the infrastructure can carry. This point was most famously illustrated in the iconic Munster Planning Department photos that just show how much space people take up when they're on bicycles, cars, and on buses. And those cars in the center scene are pretty much bumper to bumper. You cannot physically fit 72 vehicles in the same space that you can fit 72 people on a bus. In the urban areas, the space is at a premium. That's what ultimately matters. So I wanted to set the stage for sort of what we can expect from automated vehicles, because now I'm going to talk about a very specific application of vehicle automation, really targeted towards what we realistically can expect in the not too distant future with realistic capabilities of the vehicles that are being launched. So I'm asking this question basically, are there any questions, are there any settings in which maybe a simplified version of a self-driving car, a low-level automation vehicle can solve some problem that we'd be caring about in terms of traffic engineering? And I also want to touch on what the capabilities of the current vehicles that are on the roadways today are capable of doing in terms of helping us out in traffic. With those points highlighted, I'll pivot to the last part of this talk, which is really getting towards what we're working on right now, which is trying to test out these concepts at a much larger scale on open roadways. So what can you expect when you have a small number of autonomous vehicles? Well, if you're the only vehicle on the roadway, even if you're operating at a complete level 5, brain off, feet off, hands off capability, you're going to be stuck in traffic just like everyone else, right? When you have a very few number of vehicles out on the roadway, there's a limit to what you can practically accomplish. So our work has taken a slightly different pivot. What we've been looking at is trying to change the emergent properties of the flow. This video is of an experiment that was conducted in Japan in 2008. You put a bunch of vehicles on a track, they drive around in a circle. There are no geometric bottlenecks here. There are no lane changes. You just have humans doing what humans do. There's too many vehicles on the track. One small perturbation in the flow turns into a larger perturbation, which eventually turns into a stop and go wave, or sometimes referred to as a phantom traffic jam. You have this collection of stopped traffic. These cars race around the track, get stuck in the jam, and then race around and get right stuck in it again. And this is a fundamental characteristic of traffic flow when you have humans driving at traffic which is sufficiently dense. Now, this happened on a circular track. It's nice for an experimental setting to actually visualize the phenomena, but this also happens on open roadways. This is a video shot in Georgia from a traffic monitoring camera, and you can again see this same kind of collection of vehicles that are stopped, even though there are no vehicles in front of them. That kind of very fast moving traffic, very slow moving traffic, very fast moving traffic. It's bad for energy. It's, I would expect, I haven't seen any statistics on it. I'm sure it's bad for safety. All right. And that's just a fundamental property of sort of humans doing what humans do. To try to explain what's happening, you can think about these phantom traffic jams as a result of something called string unstable traffic. String unstable traffic qualitatively is when you have all these vehicles, they're traveling initially at some ideal uniform speed and spacing. There's some perturbation to the system. One driver is not quite exactly at the ideal speed spacing portion. The driver behind them recognizes that a mistake has been made, but by the time they recognize the vehicle in front is slowing down a little, they have to slow down a little bit more to avoid collision. Of course, the vehicle behind them does the exact same thing, reacts a little bit late, sees that the slowdown is occurring, has to brake harder than the vehicle in front. And you have this perturbation, which is sort of propagating against the direction of travel of traffic. And as it propagates to vehicles behind, the amount of control or the amount of reaction that these drivers are having to do is getting larger. If the traffic is less dense, or drivers have different driving profiles, those perturbations, rather than amplifying as they pass backwards in the traffic platoon, can actually dissipate. And so if you are able to design ways to have the vehicles drive that can result in something that we can eventually mathematically check, which is known as string stable traffic, we can dissipate these types of disturbances before they turn into full-fledged stop and go waves. So with this idea in mind, we repeated the experiment from the researchers in Japan. We got a collection of vehicles on a closed track. We told the drivers to drive as basically following the vehicle ahead. And the experiment is set up with one small difference, which is this vehicle that has the black arrow on top of it is a $300,000 automated vehicle. Currently, it's being controlled by a human. Now that the arrow is red, its speed is being controlled by an algorithm whose sole job it is to dissipate the stop and go wave that was in the video. And you can see as the experiment continues to run, that one vehicle is effectively pacing all of the other vehicles on the track. Instead of having the high volatility, high speed fluctuations that was characterized at the beginning of the experiment, when that vehicle is driving at its ideal speed, it ends up reducing the oscillations of all the vehicles on the track. Well, why should you care? Not only is the traffic smoother, but in terms of the fuel that is consumed in the stop and go wave period to the smooth flow has a 40% lower fuel consumption than the stop and go does. In other words, that one vehicle controlling traffic that was made entirely of other human vehicles, human drivers, real experimental drivers with data collection devices installed in their cars. We measured the fuel consumption in the stop and go waves and compared it to when the vehicle was pacing the other ones effectively. And we were able to reduce the fuel consumed by all of those vehicles by 40%. Okay, this should come with a huge disclaimer, right? You can't magically get a 40% improvement in your fuel efficiency just by getting rid of phantom traffic jams, because if you're driving on an empty roadway, no jam exists, I can't do anything to make that more efficient. And similarly, if the roadway is completely jammed, again, no stop and go waves, I can't really do much there either. That measure of improvement is measuring what would happen if you have a stop and go wave compared to what would happen if you eliminated that stop and go wave. But still, I think this is noteworthy, right? This is basically showing that if you control the cars correctly, you can actually get real benefits to the traffic flow overall. So how does that work? Well, what we end up doing is building a very simple model of the way that humans drive and then modify it to be able to implement in a control vehicle. So the way that humans drive, we assume that we have a model of acceleration, and the acceleration of the vehicle, it speeds up or slows down, is some function of the information about the car ahead. How far apart is the car ahead? That's the space gap. What's the relative speed difference between the car ahead and your current vehicle, and how fast are you currently traveling? There are a huge variety of models that all fit this type of form known as car following models. It doesn't really matter which specific model you use to describe how humans drive. What's important is that you end up basically with a model for each of the vehicles. And if you put all these vehicles on a track, you'll end up with something like 2 in-state variables that describe the dynamics of the system. So the position and velocity of vehicle 1, the position and velocity of vehicle 2, and so on, until you've described all the different vehicles, all coupled together through these dynamics that are written in some kind of car following form. The models are nonlinear, but they can be analyzed. And the way that we analyze them is actually by linearizing those dynamics and then looking to see if we change the behavior of only one of the vehicles on the track, instead of driving like a human, we add some additional term to force that vehicle to also relax to some stabilizing vehicle speed. So this you can read as the automated vehicle, vehicle J. I want to try to match some desired equilibrium speed on the track. Kind of think of it as the equilibrium speed. It's not quite the same thing, but close enough. Think about how long it's going to take the car in front of you to drive around the track. It's going to speed up, slow down, speed up, slow down. You could cover the same distance in the same amount of time by driving at the average speed, and you would have a lot less variation in your speed, right? So you can think of the equilibrium speed qualitatively as that. It's not mathematically the same thing, but it's not too far off. So if you kind of knew that speed of the vehicle ahead of you, how long it's going to take to get some distance, you could try to drive not just like the human in front of you does, otherwise you'd make the same waves, kind of relax your speed to try to drive at something more steady. And if you do this, you can mathematically prove that it's possible to choose some coefficient C, some kind of gain parameter, such that for the 22 car vehicle system, you can stabilize the vehicles. You can choose the eigenvalues, the dynamics of the system, all in the left half plane, and everybody's happy. Okay, so a little bit of kind of the theory behind how we made that experiment work. Now, in terms of what the commercial cars do, right, there's a lot of discussion about the higher order, higher level automation vehicles, but the ones that you can buy on the showroom floors today are the driver assistance and partial automation systems. Basically, adaptive cruise control is a very common feature that takes over the longitudinal control of the vehicle, it takes over the speed, makes sure that you don't collide in the vehicle in front just by driving at a steady 70 miles an hour. It will adjust your cruise control in such a way that it responds to the vehicle ahead. And increasingly, cars are coming with lane keep assist features that basically help you steer the vehicle back in the lane If you're steering at the same time you're controlling the speed, then you're operating at a level 2 vehicle automation system. And these vehicles, are pretty much pervasive in the US vehicle fleet. So you take the 20 best-selling vehicles, this is from 2018. At that period, 16 of the best-selling 20 cars either had adaptive cruise control as an optional or a standard feature on the vehicle. So these automation systems are already out there. And so it's really interesting to try to ask the question, well, what do these automation systems actually do? And how do they compare to humans? So we were fortunate to have an opportunity to collaborate with Ford on an experiment where we went to the Michigan Proving Ground in Michigan, owned by Ford, and got a collection of Ford vehicles that are all running adaptive cruise control. And on their test track, we basically compared what happens when humans are driving without any kind of automation, without adaptive cruise control, and what happens when their vehicles have their adaptive cruise control or their radar-assisted cruise control on. So here you can see a video with no adaptive cruise control. The vehicles in the lead in each lane execute a braking maneuver, and then you can watch as the vehicles behind pile up and come to almost a complete stop. Now in this video, the same vehicles in front slow down at the same amount, but the vehicles behind don't go through that catastrophic slow down and stop. Now, if you're watching that video very carefully as it pivots to sell the vehicle, you'll notice that the separation between the vehicles was quite different in the human-driven video and the automated vehicle. In other words, we're running the vehicle automation systems on their furthest following setting, and that by itself, it will reduce capacity, right? We already went through that argument that if they're driving at the same speed but leaving larger spacings, that could potentially mean fewer vehicles on the roadway than what would happen with humans. But this was an interesting example to just try to understand it qualitatively as a video of what potentially could happen with vehicle automation compared to what human drivers do. And this really got us more interested in trying to put a little bit more formalism behind this question to figure out how good these adaptive cruise control systems can be and what their limitations are. So again, we start with a model that describes the acceleration. Think of the second derivative of the position of the vehicle as some mathematical expression that's trying to do two things. The first term here is trying to relax the space gap to some amount. The amount that we're trying to do, we're trying to follow some time headway tau. You can think of time headway tau as like if you've ever been to a driver education school and they told you follow the vehicle ahead by 2 seconds. What they're really telling you to do is follow the vehicle ahead by some amount tau. Well, you multiply that by your speed and that converts to a distance. And so what we're really checking with this thing is how close away from the 2-second rule are you driving? Now you can change tau to be 3 seconds or 1 second. That's a parameter in the model. But the goal of this part of the thing is accelerate or decelerate so you're getting closer to that 2-second rule specified by tau. The second term here says, well, I'd also like you to accelerate or decelerate to match the vehicle speed ahead. So that's the simple model of adaptive cruise control. There's 3 parameters in this model, K1, tau, and K2. The parameters are basically chosen by the control engineers to describe how they want the vehicle to perform. It's mathematically convenient that you can take a car following model of this form. This is a model for adaptive cruise control. And if the coefficients K1, tau, and K2 satisfy some mathematical expression that was derived by Wilson and Ward that actually tells you whether or not this car following dynamic is spring stable or not, you can check to see if the system is spring stable or not. Let me kind of give you another way of saying it. So I give you this model. If you tell me what the parameters K1, tau, and K2 are that were used to describe how this vehicle operates on the roadway, I can plug it into this function below here. And if the left-hand side is less than 0, I know that this is a vehicle that is going to dissipate stop and go waves rather than create them. On the other hand, if this expression is not satisfied, there exist at least some disturbances that these vehicles will amplify rather than dissipate. This type of insight about how these adaptive cruise control vehicles work and how car following dynamics work is a wide literature. And it was basically separately derived in 2 communities that have since converged. As soon as people started driving vehicles, a lot of the work that was done by the core traffic engineering scientists of the time were interested in putting vehicles together in platoons and understanding the nature of how humans drive. And very quickly, as soon as car following models were being proposed, it was identified that these types of string instabilities could exist. And at the same time, there was a large group of people working in the control theory community that were also interested and whether or not it would be possible to automate these vehicles. And they started recognizing the same types of issues, that if you wanted to specify to vehicles, I need you to follow at a fixed distance to the car ahead rather than a fixed time headway. So that would be something like, I tell you, follow the vehicle ahead by 60 meters or 10 meters or 5 meters. That's a fixed distance. That's actually different from asking you to follow 2 seconds behind the car in front. It's actually, for string stability, very important to do the latter, to specify controllers based on how many seconds behind the vehicle ahead you would like to follow rather than the distance. Practically what this means is that as the speed of the platoon is changing, the length of the platoon will change. At lower speeds, the vehicles will get closer together, and at higher speeds, the platoon will extract to maintain that 2-second separation distance. But if you do that, it's provable that you can design adaptive cruise control systems that will be string stable. In other words, they will not create these types of phantom traffic jams. But we found that there was a pretty large gap in the literature in terms of how current automation systems were actually performing. The first paper I could identify was from Milanes and Schlautover, who were interested in designing connected adaptive cruise control algorithms and just happened to offhand mention in their very interesting paper that, oh, the commercial vehicles we started with are not string stable. And so you need to put this type of connectivity on vehicles. Well, kind of with these two ideas in mind, the paper that Milanes and Schlautover had published and this experiment that we had been thinking about with Ford, we decided to do a lot of additional testing. And the setup was that basically went out to the desert in Arizona with some of our collaborators. We ran a big platoon of vehicles that are all running adaptive cruise control, no communication between the vehicles. And so the lead vehicle will execute a slowdown maneuver. All the vehicles behind are identical adaptive cruise control vehicles. We want to understand whether or not that slowdown is basically absorbed by the adaptive cruise control vehicles, saying that they're going to be able to stabilize phantom traffic jams rather than create them, or if they amplify those slowdown events. And so a slowdown, we'd expect, if it's going to amplify a jam, the lead vehicle is going to slow down. We'd expect to see the vehicles behind, by the time they react, to slow down more than the car in front. You can see we've blurred the vehicle makes to hide the identity. It's not really important what kind of vehicle they are. Lead vehicle slows down, the vehicle behind, the lead vehicle slows down a little bit more than the vehicle in front. The vehicle behind it slows down further. You can see as the video continues to elapse, the vehicles towards the end of the platoon have to slow down significantly further than the lead vehicle does. The last vehicle in the platoon actually needed to slow down below the minimum operating speed of the adaptive cruise control system. In other words, this driver in this last vehicle was told that if the system disengages the adaptive cruise control, please pull out of the experiment. And that initial, I think it was about a 6-mile-an-hour slowdown event, caused that last vehicle to slow down more than 25 miles an hour, showing that for that particular make of vehicle, it is not a string stable adaptive cruise control system. Well, since then, we started testing a lot of additional vehicles, and every vehicle that we've tested so far has the same problem. There exists at least some disturbance that these vehicles will amplify rather than smooth out. And the way that we did this is basically taking these vehicles, driving them through more than 1,000 miles of data collection in a very controlled setting, where we could see how it responds to different things that happen to the vehicles ahead. We take all the data, we calibrate a model, and then with those models calibrated, we can check the string stability condition using that mathematical condition I presented earlier. We then later test the sensitivity of these models to make sure that, since the model is an approximation and our data collection has errors in it, is it possible that, there's another model that fits the data just about as well as our current model does, but that would give us a different answer in terms of the string stability? If so, then we can't reliably say that the vehicle is string unstable. What we can say is that our data is not representative enough to make that decision. What we found out by setting up a formulation of an optimization problem where we basically say, give me the best possible parameters that fit this data first and learn that the models are string unstable. We then later go back and say, how much worse would the model need to be in order for you to give me parameters that are string stable? And depending on the vehicle, the make and the model, and the time headway setting, we found that we needed to increase the error of our model fit anywhere between 5 and 30%. In other words, we pretty reliably know that these models are in fact string unstable for some perturbations. So the takeaway so far is that I've shown you an example of a video with a $300,000 autonomous vehicle that we controlled. We designed everything the way we want it to be, and we could smooth out phantom traffic jams. One car in a collection of 20 on a track. And then I've shown you some optimistic videos relative to humans and some additional information that says that the vehicles that are out there right now are not going to be the magic elixir. They're not going to be able to solve the presence of these phantom traffic jams. They'll still exist, that all the vehicles we've tested so far are string unstable. So that really gets to the last piece I want to talk about, which is what we can do at scale. We've really tried to take these couple ideas, what can be done on a single autonomous vehicle on a closed course, what can be done with the commercial vehicles, and try to figure out how are we actually going to get this to the level where a car company would actually care. Every time I show the Ring video, you know, the common criticisms are pretty obvious, right? It is a closed course. The drivers, you know, had to go through training before they could participate. There are no lane changes. If you leave too large of a gap, well, isn't a human driver going to cut you off and prevent the ability to do the control? Yes, 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 and yes. These are all real issues that would need to be addressed. And so what we've done is tried to figure out like how to take these concepts, recognizing that the commercial vehicles have all kinds of features on them already. If we could just modify the adaptive cruise control systems that are already on those vehicles in small but important ways, we might be able to use a huge fleet of them and put them on an open freeway and try to actually get to the core of the issue, dissipating phantom traffic jams on real freeways. And so that's our project goal. The project name is CIRCLES. CIRCLES is in fact a coalition of 5 universities, more than 45 researchers, 2 OEMs, Toyota and GM, and the Tennessee Department of Transportation, where we're trying to tackle some of the scalability issues. The first scalability issue is that we need to be able to modify basically stock adaptive cruise control equipped vehicles to have any fighting chance at building a fleet of 100 plus of them. We don't have Waymo scale budgets, so we need to be able to cheaply control vehicles that don't require us to put hundreds of thousands of dollars of sensors on the vehicles to be able to control them. And so what I'm showing a picture of is our lab Toyota RAV4 vehicle that is now capable of reading the radar information off of the stock radar sensor on the vehicle. It's pushed through the car communication network, which is known as the CAN network. Well, CAN, the controller, the CAN is the name of the network. It's got all kinds of information from the sensors on that vehicle. And it also offers us the ability to actuate the vehicle. We can overwrite the stock adaptive cruise control system in that vehicle. That's really important for a lot of other car following experiments that we're doing that have nothing to do with traffic flow smoothing, where we're just trying to understand the nature of human driving behavior. I show you a couple of pictures here of what car following experiments looked like in the early days of GM and others that were doing car following experiments. My favorite are this thing called the GM fifth wheel. It's a bicycle wheel they attach to the back of vehicles so that you could easily measure the speed of the vehicle and basically log the information about the speed of the vehicle. And the GM car follower was basically a giant grappling hook that physically connected the 2 vehicles together. The cable was under tension, and so you could measure the space gap between the vehicles as the cable was pulled out and pulled back in as the vehicles adjusted speed. Well, that is obviously extremely difficult to kind of test on an open roadway. Because we have the ability to read the radar data directly off of our lab vehicle, now we're basically putting in a Raspberry Pi that's capable of logging relative velocity and space gap data directly from the car's stock sensors. So you basically pay for the data logging, you don't pay for any of the sensors that need to be installed on the vehicle. So this is just a short video of us running a small experiment in Nashville where you can see the relative velocity and the space gap dynamically changing on the left and right respectively as the vehicle ahead gets further apart and closer together. So this is a very important way to be able to collect data at scale. So in one piece, we're working on how do we get low cost ability to sense and control vehicles. And on the other hand, I need to figure out ways that I can measure the consequences of putting these vehicles on the open roadway. Unlike the circular track, which is very easy to film with a single camera and measure the features of all the vehicles. Moreover, we can install, loggers in the cars in the experiment. On an open freeway, I don't get to control any of the other vehicles on the roadway. I don't get to install any devices inside those vehicles. And I can't, from the vehicles themselves, measure the full information about the traffic state. So we've been trying to tackle this problem, really taking inspiration from the seminal next generation simulation project known as NGSIM. One of the data sets, which I'm showing here, was collected on the Interstate 80 freeway in Emeryville, California, where they stuck 7 cameras on a 30-story building, and that allowed the creation of 3 15-minute long data sets that track the trajectories of all the vehicles on the roadway. This data set was, of course, fundamental in terms of microscopic traffic simulation, and has been cited at least 2,500 times for the value of the data that gets created. But of course, every time we bring these types of things up, we constantly run into the same issues, right? The data set is too short in length, and it's too short in duration. Everybody wishes that we had more of it in all possible ways. So kind of recognizing that, we've been working closely with the Tennessee Department of Transportation, who is investing on the order of $100 million on a major freeway just here outside of Nashville, Interstate 24, which is experiencing tremendous growth and has no control infrastructure on the corridor. The arterial traffic signals are not timed. The ramps don't have meters. There's no variable speed limit control. And it's actually a relatively dangerous corridor. There's a large number of crashes, and some of them are fatal. And so they're deploying a lot of technologies to try to make this corridor a little bit safer to commute on as the growth in the area is continuing to accelerate. And so what we're trying to do is basically deploy, in the same style of NGSIM, a large number of very high resolution, 4K resolution video cameras that would give us the same type of information that we got from NGSIM, with kind of 3 goals in mind. We'll be able to better understand how the active traffic management technologies that TDOT deploys on the freeways works with regular drivers. We'll be able to use that information to hopefully improve the reliability and, importantly, the safety of the corridor. And we also have interest in testing our connected and autonomous vehicle technologies. So in the fall of last year, during the pandemic, we were able to work with a number of firms in town and the Tennessee Department of Transportation to test this concept of basically getting cameras high in the air permanently so that we can continue to collect information that can help us unlock these wave smoothing, active traffic management, and safety technologies. This video is showing some work that we did on an early Sunday morning with a team of more than, I think, 50 folks that were on the construction side, helping us raise these 110-foot tall poles spaced every 500 feet on the freeway and this heavy infrastructure. And at the top of all these poles are pods of 4K resolution cameras that point down at the roadway and allow us to collect data. To give you an idea of kind of how this system works, this is now currently operational. We have 3 poles that you can see on the left here that each host 6 4K resolution cameras. There's a fiber network that connects these poles to a hub facility about a few miles down the freeway, where we've installed computers that can run computer vision tracking algorithms. Those computers receive the video data from the 18 total cameras that all have overlapping fields of view. And on that video data, then we run computer vision tracking algorithms to get rid of this high resolution, very impossible to save because it's so large data set, and get what we actually care about from the traffic flow theory perspective, which is the trajectories of the vehicles, basically their position, their velocity, their acceleration as a function of time as they pass through the corridor. This system is currently collecting trajectory data on something like 180,000 vehicles a day that pass through this corridor. On the computer vision side, there's actually quite a bit of advances that have been made since the time of NGSIM. In fact, now detecting cars in a frame is a relatively solved problem. It's not perfect, but significant improvements where we can use detectors like YOLO, ResNet, a bunch of other object detectors that are pervasive in the computer vision literature that basically do the following for you. They draw a bounding box around the vehicles in the scene. Well, in terms of tracking the vehicles, I don't just need a bounding box in pixel space. What I need to know is that from one frame to the next, this bounding box in frame 2 corresponds to the previous bounding box in frame 1. It's the same car, just it's moved, right? So there's a detection and step first, and then we have to associate those detections with the same vehicle so that we can track. As we associate these detections from one frame to the next, the final step is to take this information and get it out of pixel space. I don't need that a bounding box on a car is from pixel whatever to some other pixel. I need to know on actual real world coordinates where those bounding boxes correspond to. And so there's a very standard approach in computer vision to convert from the image plane, basically what the camera sees, to the road plane where the vehicles are located. just to give you an idea of what this looks like, you can see the squares that are tracking these vehicles as they pass through one of the cameras. And then basically using the approach I qualitatively described in the last slide, we can convert that into trajectories, where you can see kind of drawn on top of a Google Map layer here, the tails of these vehicles, is identifying that it's the same vehicle that we're tracking as it passes through the roadway. And the next step that we're working on is not just putting square bounding boxes on cars, but kind of pushing to the limit of what is capable of occurring in modern computer vision, which is actually putting 3D bounding boxes on these vehicles in real time. So the setup, of course, is that we've got 18 cameras of data currently that are pushing all this video data to us, and we need to be able to put these bounding boxes on these vehicles, not offline, but in real time, meaning we've got to be able to calculate very, very quickly. This is part of what drives the cost of doing computer vision up pretty significantly, because you more or less need at least one GPU per camera to run these algorithms, unless you take advantage of some algorithmic techniques to speed this up, which our team is working on. So kind of to give an illustration of where this validation camera network that we just built sits, in terms of NGSIM, the data set that I showed on I-80 has about 1,800 vehicle miles of data inside of it. Basically, you take the total distance and the total time that all the vehicles have, a total distance, and the total number of vehicles that travel that distance, and it gives you a vehicle miles traveled measure of how much information is in that data set. In 2018, there was a recent set of experiments that were done by flying drones over freeways, and they were able to collect 25,000 vehicle miles of trajectory data. The challenge with drones, of course, being that they have to recharge the battery, right? So you only get limited flights. With the validation system that we just deployed in December of last year, because of the large number of vehicles that pass through that sensor network, we're going to collect on the order of 16 million vehicle miles of data just from that network alone. Since we've completed that validation system, you can kind of see it in the name. We call it the validation system because we've now been working with the Tennessee Department of Transportation to complete designs that would allow us to expand the sensing infrastructure to the scales at which it would matter for experiments. And that we really are looking at somewhere between 2 and 6 miles of freeway that we're planning to instrument. And I'm hopeful that in the not too distant future, we might have some more progress on that front in terms of actually being able to start construction to get the rest of this network deployed, so that we can have a fully instrumented freeway that is capable of understanding, when we put automated vehicles out on the roadway, how those automated vehicles are affecting the flow, both locally near the vehicles that can be measured, as far far downstream outside the field of view of those sensors. And you can kind of think about it in the following way, and I'll wrap up here in just a second. If you've got a vehicle that is driving very cautiously and creating lots of lane changes in its wake, but you can't capture that, that's not actually a control algorithm you'd like to deploy. So this sensor network is really designed to try to capture that. So the take-home messages I have for you are really just trying to, at the broad level, recognizing that automated vehicles are not going to solve all of our mobility problems, full stop. But if we think carefully about the scope in which we deploy those technologies, I think that we can actually help improve traffic flow in modest ways with modest penetration rates using modest technology, i.e. stuff that's not that far away from what is commercially available. And we've really been pushing hard in terms of the vehicle technologies and the test beds that we can put these things really in reach to try to drive these technologies into vehicles that are being released today, long before the fleet is fully automated, long before the fleet is fully electrified. We might be able to get some gains on real features in the not too distant future. I want to wrap up with my last thoughts of career advice. I was asked to speak about that. I think everything that I can share with you so far has been really the success of the great people that I have been surrounded by. I got interested in traffic engineering as a high school student. Susan Banbury, the planning engineer in Westerville, Ohio, gave me my first job, having no clue I ever wanted to do anything about transportation. She taught me how to do turning movement counts and time signals in my hometown. That got me interested in transportation as a career. I eventually found my way to UC Berkeley in grad school, where I had a chance to work with Alex Bayan and Quinn Jacobson at Nokia Research Center, Palo Alto, who taught me how to code, how to do mathematics, and how to basically use emerging technologies, at the time GPS-enabled cell phones, to do meaningful things like estimate traffic conditions. The experiments I showed you today with the ring were done by a huge team of people, professors at Rutgers, Benedetto Piccoli, Temple, Benny Seibold, a new hire at UC Berkeley, Maria Laura Delamonica, and Jonathan Sprinkle, who's taught me everything I know about autonomous vehicles. You know, it's really a collaboration that allows us to do these exciting things. Even in Nashville, socially distanced, it was a team of phenomenal people at TDOT that have really enabled us to try to move the ball forward and tackle hard problems. So my career advice for you is whatever you end up doing, whether it's working in industry, government, academia, make sure that the people that you're working with are people that can help elevate what you're trying to accomplish. At least in my career, that's been the single most important thing that has enabled me to expand what I've been able to work on. And as a faculty member, my great people are the students that I get to work with, and I'm extremely fortunate to have what I think is the best research group in the country. And that's entirely due to the quality of the students that I get to work with. It makes it fun to sign in to Zoom and Slack every day. So with that, thank you for your time. I'd be happy to take any and all questions that you have.
Thank you, Dan. And really, you showed that working in traffic flow is not just the computer coding and look at the mathematics, but a lot of real life exciting things to do. And I really like the experiment that you have done, and it's really impressive for the last project. And I was wondering, like, what's the coverage distance for that last pilot study?
When I said I was inspired by NGSIM, I meant it literally. It's the exact same distance as the NGSIM setup. It's 1,600 feet. Yeah, basically the way that we set that up was a way to test like the pole spacing, the camera technology, the fiber network, how many CPUs and GPUs we needed so that we could get an estimate of a reasonable cost to deploy a lot more of that. We've been extremely fortunate that the chancellor at Vanderbilt and the commissioner at TDOT have been really champions of trying to put in technologies and test beds that might allow us to meaningfully learn from what's happening on that freeway. You know, recognizing that there are many great academic and commercial test beds that allow you to do things like test extremely experimental technologies where you don't want to interact with human drivers. Right, like I'm thinking M-City is obviously one of the pioneers in the academic setting, but there's a gap, right? And the gap is that once you've got these technologies kind of refined, you need to understand how they interact with all the other human drivers that are on the roadway. And for that, simulating real traffic is a very expensive endeavor because of the number of people it takes to create traffic. And so there, we really kind of set this up as a validation environment where we could test the core technology concepts with the goal to roll this out really to a full 6 miles of the freeway when we're all said and done. How long that's going to take and how much it's going to cost is an open question that we're currently working on trying to align the funding and the partnerships needed to make that a reality. But that I hope to have more news on soon. Currently 1,600 feet is the short answer.
All right, great, thank you, Dan. So now we open up to question and answers. And as we usually do, we'll first have our students ask the questions because this is part of their course. And then once we're done with the students, and then our outside audience can ask their questions through the Q&A feature of Zoom. I already saw a couple of questions in the Q&A. So let's open up the chat. And also for our students, if you have questions, you can use the raise hand feature. So I can see who raised the hand, and then I can kind of moderate the question and answers. So do you have any questions from our student audience?
Hi, thank you, Daniel. It was really awesome and exciting presentation. I have a quick question. I know that this technology, you have tested it on highways, and it meant to be to smooth the traffic flow on freeways. But I was curious to know how much of it, or to what extent we can use this technology to increase the safety in urban streets where the bike lanes are presented, or the bikes are sharing the road with cars and this type of situations?
Yeah, that's a great question. I mean, just to make sure I've caught the gist of it, right? Everything I showed today was very much focused on freeways. And I shamelessly point that out because I think freeways are meaningful problems to solve. And yet they're not all the problems. As a regular person who walks on a street that has no sidewalks, I live in a community that is missing many of them. Most of the roads in Nashville do not have sidewalks. That's part of the challenges we have with transit that I kind of opened with. There are a bunch of problems where I think automation could potentially help in more urban environments on arterials and on surface streets, but it's a little bit more tricky there, right? So, what's actually on vehicles today? You can get vehicles today that have forward-facing cameras mounted up in the rear view mirror, and that forward-facing camera can run a couple different types of computer vision algorithms. The nominal one is to detect whether or not you have lane markings. And if you have lane markings, then I can steer you in the center of the lane. But increasingly, as the technologies on detection have been getting better, they're able to identify things like pedestrians. And whether or not you want to brake based on detecting a pedestrian or not becomes a little bit more of a subtle issue, right? Because you need to be confident in what you see. You've got a radar sensor and a camera that can help you make that decision. But full stop, yeah, if you can detect pedestrians, you can help those vehicles avoid collisions that might otherwise occur due to distracted driving, right? But the vehicle automation is still not going to change the fundamental physics of how fast cars drive and what happens when you collide with pedestrians, right? The Vision Zero stuff is not about, it's maybe a bit too strong of a statement, but right, Vision Zero tells us things like, if you have a person that is hit by a vehicle that is moving at a high rate of speed, the chances of fatalities will increase. And so unless you're going to take a hard edge automation to do things like slow down vehicles, in addition to adding the safety features that might allow those collisions to be avoided even when humans make mistakes, it's a lot harder problem. You need a lot more context awareness. You need a lot more predictive analytics in terms of what the information you're seeing right now might lead to something in the near future. It's not good enough to, in some cases, you can't, what's the right way to say this? To drive a truly safe vehicle, what you'd like to be able to do is you'd like to be able to have enough sensors, no different than you would for some of the safety calculations we do for human drivers. You'd like to know sort of what is the field of view of what you can see, and can you perceive information, interpret that information, and react to that information fast enough to stop your vehicle before you collide with whatever might be in the environment. If you want to try to drive a provably safe autonomous car or automated vehicle technology, in addition to making sure that you always detect the pedestrian, you also have to be able to kind of calculate the safety envelope and make sure you're not driving too fast, such that anything that's on the periphery of your sensor field of view could potentially get into your field of view and cause some challenges. And right now, that just basically means you need to install a lot of additional sensors, number one, and two, you need to drive extremely conservatively. And the question is whether or not you could even get some of those technologies on vehicles if they have to drive ultra conservatively. So that's a long way of saying that the problems in the urban areas are harder. And as a consequence, I have less to say about them. I think the freeway is a constrained thing where I think I can meaningfully make an improvement without having to wait for computer vision algorithms to improve.
Thank you.
I think Ray's question was a very good one. I think it's one that a lot of people in this field also struggle with. I'll stick with just freeways and just focus on a question that I have in regards to that. So I originally I came from the Netherlands, started driving out here in California, and one of the things I noticed is that we don't have, for example, variable speed limit signs. I was wondering, kind of being realistic in the future here of vehicle automation, do you foresee that system having variable speed limit signs being integrated into vehicle automation? And how do you foresee this change happening between having partially automated or autonomous vehicles and still having people be in control. And we can just talk about the freeway if you'd like. So it's kind of like a control system. How do you foresee that change happening? Would this be a lane that's dedicated to autonomous vehicles, or do you have any kind of vision on that?
Yeah, here's the vision. I don't know if it's possible, but here's the vision. The vision is that basically, without dramatically changing anything on the vehicles that are currently being sold, like rewrite the control logic box, that's it. Don't change the sensors, don't add connectivity, don't require anything else. You just turn on adaptive cruise control. And instead of designing an adaptive cruise control, which is strictly speaking, optimized for fuel efficiency of that vehicle, rider comfort of that vehicle, it has also taken into consideration the consequences of putting in lots of those vehicles into the roadway, i.e. the emergent properties, i.e. string stability. And in theory, it's 100% possible to do. Now, the problem is that in theory, cars drive according to ordinary differential equations. In practice, they're a lot more complicated than that. There's gears that shift, there's vehicle dynamics, there's road grade, there's a million other things that make it not so simple to describe it as a 3-parameter ODE. But the vision is basically just that if we can, maybe another way of saying it in my own words without putting it into an OEM explicitly, if you were able to improve the fuel efficiency of other vehicles which are not your vehicle, ought you be able to get some credit for that? No different than vehicles that are if you're trying to get your EPA rating and thinking about like the markets where Tesla trades their EV credits, car companies presumably would care about trying to make a case for the fact that they're reducing fuel consumed for everybody, not just themselves. And there's a whole lot of political things that come into play there. So I'm not going to basically try to work out all the details on the Zoom call here, but that's a possibility. And I think my point would be like, if I can design something that nobody really notices what's going on, but just makes these phantom jams not so frequent on the roadways, I mean, that's a win for everybody. What gets more interesting is to your question about the variable speed limit, right? So now what happens if you start imposing harder controls on what you want vehicles to do, right? That it's noticeable to the driver that the control that is being implemented on the vehicle might have some other objectives in mind, like enforcing a variable speed limit. If a variable speed limit is advisory and everybody drives right past it, ignoring it, that's not a very useful control to manage freeway traffic. The minute that you force someone to drive according to that, and I'm thinking like using communication, 5G, DSRC, whatever you want, tying that into the vehicle and then adjusting the vehicle speed, and now I'm driving at the speed limit posted from the VSL while everyone else is doing whatever they want, I don't want to turn that on. I mean, not me personally, but I can imagine how there'd be reactions from a lot of people that would not be interested in having that kind of technology. And then you go right back to the car companies who are not interested in selling features that consumers don't want. So it's kind of a delicate, line to walk in terms of how aggressive you want to be in terms of what you allow those vehicles to do, and how little you're willing to accept in terms of performance benefits because you're trying to accommodate all these other factors. I'm going to start with the small improvements without anybody noticing, and then maybe see if we can't get a little bit more ambitious with more exotic controls that might give us a little bit more control overall in terms of what's happening on the roadways.
Yeah, because I could see how, if you're using a VSL system, how this would be very appealing to make this part of that and use the GPS of the car, or use some kind of centralized system to monitor that as well. Yeah.
I'll just leave with it really is kind of this issue of the mixed autonomy, right? If I'm watching Netflix in the car, I could care less what's happening. Yeah. But as long as I'm still like actively paying attention, trying to fight rush hour with everybody else that's around me, then I think it's going to be a trickier business to try to get some of the more exotic control policies implemented on commercial vehicles. We can do it for demos, but they won't make it over the sort of theory to technology transition.
Thank you, Daniel.
Perhaps one of the strategies to have the highway patrol fleets have some of the autonomous vehicles and deploy them, and that will have a calming effect on the roadway, and also would have the anti-phantom jam capabilities.
I would build on that comment in two aspects. We've had exactly that conversation with some of our partners in the state here about what this would, if there are other vehicles that we would intentionally put out that we would have more control over, which is one aspect. The other aspect is that one I'm maybe partly optimistic about actually is that, if we were able to do something like this on freight vehicles, the big trucks, that actually might be a more natural place to do it. The truck drivers, anecdotally, from the video data we've seen so far, they are exactly the type of wave smoother you want. They are sitting up higher. They can see further than the cars directly in front of them can. So they can, not race into a jam that they know is present. And they have a vested interest in driving in a fuel efficient way. So, so those vehicles might be more natural vehicles to exploit control and automation technologies that are coming anyway, that would have a dramatic potential consequence on other human-driven vehicles on the roadway that are not freight vehicles. It's still a tricky business dealing with freight broadly, but I think there might be a possible additional pathway through the freight vehicles to do something on that line as well.
Yeah, the only potential problem I can see that the freight vehicles normally don't travel on the fast lanes. That means they travel on the right shoulder lane and the second. And so by their controlling them, and you create a sort of another level of complexity, because the passenger cars, they could try to pass and squeeze more lane change and so forth. That could actually increase the chaotic maneuvers, unless the trucks moving on all the lanes on the highways.
I have seen a truck in an HOV lane in Tennessee. So, but I think your point is well said.
Okay, any other questions from our student audience?
Hi, Daniel, I had a question.
Go ahead, please.
Yeah. Thanks for the presentation, really interesting. Just wanted to ask, you talked about the levels of automation. Have you also looked at what might be the critical minimum AVs you would need per density of vehicles to actually ensure that this traffic is stable? And second question is, have you also kind of got a sense of what mix of the different levels of automation might we need to get incremental improvements on the parameters that you are talking about?
Yeah, I will take those in reverse order. What mix of levels of automation do we need in order to do the types of things I'm showing? Yep. Level 1. I don't need anything higher. That's the easy one. The next one was how many of them do I need? I think was the gist of the question. Yes. So the ring video, round number 5%. That's the starting point. Now let me unpack 5%. It's going to be higher on an open roadway. It will absolutely be higher on an open roadway. Why? Well, on the ring, I had an automated vehicle that was controlled, that was spaced uniformly amongst the humans. In other words, think of that ring as an infinitely long chain of vehicles where I've got 20 human drivers, an automated vehicle, 20 human drivers, an automated vehicle. They're perfectly uniform. In the real world, I won't get adaptive cruise control vehicles that are perfectly uniformly distributed, whatever the penetration rate is. So that's the first piece that's going to drive it up. The second piece that'll drive the penetration rate up is all the disclaimers I made about the ring, right? There is no lane changing. You don't have to deal with vehicles that cut you off as you're trying to leave a little bit larger gap or things like that. On the real roads, those are absolutely issues. And moreover, depending on whether or not drivers in Davis are kinder or more aggressive than drivers in Nashville, then it's going to get even more dependent on sort of like what else is on the roadway. I'd hope for trucks if I were trying to make my penetration rate lower, because the fact that they can see a little bit further, and just anecdotally, as we've been running a bunch of tests in Nashville, we've observed that sometimes they can actually help create smoother driving profiles than the cars in front of them. But all those things are going to be, increasing the penetration rate. So you want a round number? I mean, I'll pick one. It'll be wrong. 10%. I think it'll still be low, but more than 5. And I would maybe finally add the following piece that I think still gives me optimism, even when it's a lot less than 5%. If I'm the only automated vehicle on the roadway, level 1, running the control algorithm that I have not yet invented, that happens to be wave smoothing, the car in front of me, if it's going speed up and slow down and speed up and slow down, and I end up driving at a profile that covers the same distance, same time, but in a smoother way, then at least the car behind me has the possibility of having lower fuel consumption than the car in front of me. Now, if that person still drives speed crazy, then I've lost all ability to control, because I can't do anything about the cars behind me. But you can imagine that there would be at least a few vehicles behind every automated vehicle that might be able to capture some benefit, so that as you go from 0.00001% of the vehicles that have the right control on it to 1% to 2% to 3%, you will get increasing benefits. Even if the waves are still present, there'll be a few cars that benefit from smoother commutes. So in that sense, I think it's actually a good thing that you don't have to have a critical number to get some benefit. Basically, 1 is that critical number to get some benefit.
Thank you.
All right. I think I'll open the Q&A to our outside audience, and I have 2 questions from Lindo and a nice comment from Wes. I'll ask Lindo to ask the question herself.
My first question, I think you pretty much answered already, which was similar to the first question the student asked about when vehicles are mixed with pedestrians and bicyclists and access to public transit. My other question is, you may have already answered, is what differences are needed in vehicle automation for vehicles that are traveling with, where they interact with pedestrians, bicyclists, and people accessing public transit?
So make sure I caught the question. What differences are needed in the vehicle automation systems, basically to better accommodate non-vehicular modes of transportation?
Right.
Yeah, I mean, to me, it really boils down to, well, look, there's like 3 levels of sensing that are widely used in building these types of vehicles. There's cameras, there's radars, and there's laser scanners or LiDAR units. The LiDAR scanners are wildly expensive. The cameras are relatively cheap, as are the radar sensors. So, in the dream world, to make the truly safe vehicles, you'd want a collection of a lot of those mounted at a bunch of different locations on the vehicle. So you have full 360-degree resolution to everything that could be potentially in your environment that you might have to react to. I think the art form is sort of like, how can you keep the cost of the sensors low enough that a car company today can afford to put them on your vehicle? And that's why you're seeing most of the car companies lean predominantly to radar and camera. You're basically looking at those types of sensors to be able to measure what is going on in the environment. You have to do some machine learning or some kind of predictive analytics to understand how the pedestrians, how the bicyclists, how other non-motorized modes might potentially, where they might be in the future based on where they're now. You have to predict that they could potentially be in a collision path with your vehicle. But that problem is also something that, the Waymos of the world and the Uber ATGs, they spend a lot of energy trying to think through. So I guess what I'm really trying to highlight is there's like a spectrum of benefits for the non-motorized modes, depending on how expensive you're willing to make the automation systems on the vehicles. The more expensive, the higher the budget you put on the vehicle, the more safety you might be able to offer the non-motorized modes. You only have one forward-facing sensor, you're really pretty limited in terms of what kind of safety guarantees you can offer. But I think it's an important direction, right? That is where, all the people that are working on the hard vehicle automation problems of level 4, level 5, that's where they're focused. They're focused on the urban areas because of how hard that space is.
All right. Thank you. If I can ask a follow-up, would reducing the speed help to simplify or reduce the cost?
It would certainly simplify the design in the following sense. Like the more uncertainty you have in your environment, the bigger of a problem you've got, right? If I've got an object, I don't know what it is, I just know it's in front of me. I've got to make a decision potentially very quickly as a function of how fast I'm traveling. Every millisecond that passes is my vehicle moving closer to the target. And the slower you're moving, in the extreme case, if you're completely stopped, you can think as long as you want. You can afford for your sensor to take another sweep and detect a second time the object is still there, detect a third time the object is still there, detect a fourth time the object is still there. All those repeated measurements are giving you confidence that what you in fact are seeing is in fact a thing that you need to take evasive action on. When you're traveling very quickly, you've got the exact opposite problem. You might only get one sweep of your sensor. You get the information, there's something present. There's no opportunity for you to check to see if what you've got is a false positive, if the sensor just saw some anomaly, or if it's something that you must act on. You have no other option. You're traveling too fast. You have to make a decision now. If you wait for more information, it will be too late to avoid the collision. So reducing the speed, it absolutely makes the problem of trying to make sure you drive in a way that's safe easier. It goes right back to the challenge, though. The more you force something on the vehicle automation systems that is different than what the humans are required to do, the harder it's going to be to encourage people to adopt those vehicle technologies.
All right. Okay, and Wes Lam, he's a retired longtime Caltrans research manager. He put a very nice comment on the Q&A, and I'll read it, Wes, and if you have anything to add after I read it, and you can add to it. So the comment is, students should use Daniel Worth's presentation as a model to emulate. It is clear verbally and visually, so the audience can easily follow. His speech described the graphics, so that combination give a very understandable presentation. So this is among the best presentations I've seen from UC Davis in the last 10 years. I fully agree with Wes. And Wes, do you have anything more to add? And clearly, Dan, if you move to California or work with us, you have an easier time probably to find the money to support your experiments and to put the extra poles on probably 80 rather than 24. Yeah, I'm not sure. Yeah, Wes, yeah, go ahead, please.
I'll respond to Wes's comment. Wes, obviously honored to hear the feedback. Really appreciate the warm and kind words. I just want to thank you as a representative from Caltrans. I know I couldn't have done my PhD without Caltrans' help. You all were instrumental in a project I was fortunate to be a part of in 2008 called the Mobile Century Project. It was a partnership between Nokia, Berkeley, and Caltrans. And I remember driving to Sacramento and having a meeting about, we kind of want to make a major deviation in our research plans to do something a little bit different. And Caltrans gave us the full support to go forward. So just really appreciated the vote of confidence that Caltrans gave us then to help launch my career, and obviously the kind words today. So thank you.
Okay, with that nice note, I think if there's no more questions, we'll stop here. Any more last minute questions for Dan? Well, if not, we want to thank our speaker, Professor Dan Walk, again. And I wish everybody a nice weekend. All right.
Hey, thank you all. Happy Friday. Good luck on the rest of the rest of your academic pathways. And if there's any way I can help, obviously feel free to reach out. Thanks for your time and attention.